Tima here talking about projectile motion. I'm going to try to make this quick, but there's going to be a lot of questions on this, and that's okay. There is some math, but try to hold off your confusion about the math till the end. Some of the big equations are kind of at the end, kind of the three most important, and we'll talk about that as we get there. So projectile motion, okay, this is the idea. Basically there's two different problems here. You have your basic cliff problem, which is kind of like what we did in class with the sketch lab where the ball was dropped by the windowsills. And then we did some problems free fall jumping like the diver off the diving board. And then you have what I like to call the arc problem, which is throwing a ball up in the air or throwing a football, okay, something like that, where we actually have some height involved there. All right. So the lab, you didn't do the lab. We're doing simulation labs, which you should have done already. It's the PhET simulation lab, and that's in your um, folders on Schoology. So again, a time stop photo here. The idea is whenever we toss a ball, either it's straight up or out for a pass or something like that, we have to remember that this ball, if you will, okay, it has an initial velocity. When it reaches its very top, we assume that it has a velocity of 0 in the vertical, okay? But then it would reach the same vertical velocity at the bottom if we drew a straight line all the way across. But its horizontal velocity is constant. And that's something that you should see from doing that PhET simulation. And we'll work on this, okay? All right, so here's a good little GIF, if you will. So the green ball represents the vector of its horizontal velocity, and you'll notice the red ball represents the vector of the vertical free fall. If you notice the green, the horizontal is constant, and the red is accelerating due to gravity. Okay, and then we get what we call the parabolic motion, which is that fall, what the ball's actually going to do. Okay, so if we were able to split the ball into three parts when we threw it, the green would be what it looked like going out away from you. The red would be what it would do if it fell straight down. And then we have our parabolic motion there. Okay, and basically it all comes back down to SUVOT, but we'll get there. All right, so here are the trajectories. Okay, this is, remember, V is velocity. Okay, G is gravity. If you notice, G is constant. Okay, and then, so here's our velocity, if you will. Okay, and then we have these things called heights. And yes, we have angles, okay, and all these things. But some big words we need to get out of here are the words height. We're talking from basically the ground to its highest point. And we need to make sure that we understand the word range. And range is really just our displacement in the x direction. Okay, if there was no gravity, and this is what Sir Isaac Newton tested this, and of course didn't work, but he had a theory that if we fired a cannonball with no gravity, it would literally go around the world and hit the back of the cannon. So again, once we add that in, we get that parabolic trajectory. Okay. So again, I just like to have this little gift run here. So here's what the cannonball would actually look like. And if you actually look at what's happening, time, of course, moves forward. Okay, time is moving forward. We can get that thing to disappear there, sorry. All right, if you notice the velocity in the x direction is constant, that cannonball would hit you at 100 meters per second. Okay, but the velocity in the y keeps increasing because it is accelerating downward. Okay, this goes back to kind of our lab we did the other day where, again, just realize when people back in World War II had to drop bombs or whatever, or if a plane had to deliver a relief package or something like that, what happens is that plane has to release that bomb or package way before the actual target. And that's because since Newton said an object in motion will remain in motion, well, there it goes. It's trying to follow the plane. The funny thing is, if you look at the object from, let's say we were in a spacecraft above the plane, it would look like this. So this is what it looks like, right? This is what we just talked about, hitting the target. But if you were in the plane, that's what the bomb looks like to you, or what the care package looks like to you. It looks like it's falling straight down. And that takes us all the way back to the first chapter where I said if you were asleep in a car, okay, if you were asleep in a car, you wouldn't be moving relative to you, but someone on the outside thinks you're moving at 70 miles per hour. All right, so here we go. We're going to be getting into actual kind of suvat for horizontal motion. Well, velocity is, and we're just talking about horizontal right here. Velocity is displacement over time. Well, what does that really mean? What that means is displacement in this case is range. So this should change to range. Okay. So let me get my little marker here. Let's just write right on top here. This displacement really changes to range. Okay. And velocity in our thing, if you go back, velocity actually changes to v cosine theta. Okay, it's hard for me to write on here, but that's okay. Cosine theta. If you manipulate this formula and solve for range, so multiply both sides by t, you get this formula right here. If you were to rewrite it, it would say S, and this v cosine theta really is just v, which is just our standard problem that we've been using. Okay. So if we think about this like a golf shot for a second, all right, if you go out on a golf course and you want to drive it as far as you can, you're going to use a driver. It has a very flat head so that our angle isn't very far and our most of our energy would be in the horizontal direction. Everybody that goes golfing, if you've ever golfed, they know the 7-iron is one of the best clubs you can use because it's a 45-degree angle, which means both of our forces are equaling in both directions. So we get a nice loft, but we also cover a nice distance. And sometimes you might see people when they get close to a green, they might use like a pitching wedge or something because they want to get the ball really high in the air because the angle is higher, but they don't want to travel as far. Okay. But notice how and that's something you should have picked up in your PhET simulation. Okay. But basically, what happens here is we are left with three big equations, and that is our range equation, our height equation, and our time equation. Okay. So if a ball is thrown at an angle of 30 degrees to the horizontal at a speed of 20 meters per second, calculate its range and the maximum height reached. So we have to use these equations. We have to use our range, and then we have to calculate the maximum height. Okay. Well, for range, we need R, V, and a theta and a T maybe. Okay. Well, we have to look at this. All right. Take a second, see if you can figure this out, see if we can type in an answer, and then we'll go over it. So for the range, we actually have to figure out time first. Okay. So even though we're looking for range really high, we needed to find time. There's no time given. So to find time, we have to use what we're given. And how we do that is we list our variables because we knew that we had velocity. We know we have an angle. Okay. And we know that gravity is 9.81 meters per second. He used 10 in his solution, but that's fine. And we would find out that time is 2. Once we have time, it's easy peasy. Now we just plug in the range, and now we solve for height, which would be 5 meters. Okay, so take a second, look at that. Make sure you look at that. It's also in your book. And if you have questions on that, make sure you ask in class. Okay, a ball is thrown off a cliff with a 10 meters per second. If its cliff is 20 meters high, what is the height? Or excuse me, 20 meters high, what is the range of the ball? Well, this one might be a little tricky if you haven't been paying attention so far. Really, the question is, does the height of this matter? And the answer truly is no. Okay. The only thing that really matters is how much time is this ball in the air? So, first of all, we can figure out how much time, if we just dropped the ball, would it take to hit the ground? Okay. And how do we do that? Well, we can use 1/2 AT squared. Okay. S equals 1/2 AT squared. And if we do that, if we do 1/2 AT squared, we find that it takes 2 seconds for the ball to hit the ground. Well, now it's real easy because horizontal and vertical are involved with each other, but yet they are kind of independent of each other with calculations. It'd be the same as if I had a ball down here with a cannon and I shot it at 10 meters per second for 2 seconds. How far would it go? Well, it would go 20 meters because range is just displacement times time. The velocity or the range displacement is just velocity times time. And so we're right there. And that's how we do it. Okay. So that's a little tricky, and that's kind of what we're working on is this whole idea. So this is the famous if I dropped a bullet and shot a bullet at the same time. And we're going to talk about that here in a second. You watched the Mythbusters video on that. All right. The biggest thing is without air resistance, you should have this. People on the golf course should be able to drive the ball at like 500 yards. They don't. They only drive it like 280. And that's because of air resistance and a lot of other factors. Okay, which you did in a free fall lab. Okay, our cliff problem, again, this is more of an arc problem at an angle. Notice everything else pretty much holds true, except velocity in the y is positive, slowing down, and then becomes negative as it starts to move down. That's kind of like our problem just in our free fall chapter there that we talked about. I think it was number 5, or it was kind of a two-parter, okay? But notice the velocity in the x is still constant earlier in the week. You should have watched this video already with the Mythbusters Fire Drop, 5 parts, really explains that. Hopefully you enjoyed it. If you haven't, you need to watch that now. It is located in your Schoology folder.